Hey everyone, welcome to This Explainer. Today, we're diving straight into the fascinating mathematical anatomy behind how a machine actually learns. I mean, we hear about AI and neural networks all the time, right? But how exactly does a computer go from being a total blank slate to recognizing complex patterns? Well, we're going to break that down step by step, looking at the actual math and structure that makes the whole thing tick.
To get us grounded, let's rewind a bit to 1959. Arthur Samuel hit the nail on the head with this definition, basically outlining the ultimate goal of computer science, giving machines the ability to identify patterns entirely on their own. This idea that a machine could adjust its own internal parameters without us explicitly programming every rule, that was absolutely revolutionary, and honestly, it's the foundation for everything we're looking at today. If we quickly trace the roots of artificial neurons here, it goes way back to the 1943 McCulloch-Pitts model, which first drew this cool analogy between biological brain cells and simple logic gates. Then, skip to 1957, Frank Rosenblatt gives us the perceptron. And finally, in 1960, Widrow and Haas introduced the Adeline, the adaptive linear neuron, which really refined the underlying math and gave us a learning rule we still build on right now. Okay, here's our quick roadmap for today. 1. Meet the artificial neuron. 2. The forward pass. 3. Calculating the error. 4. Gradient descent. 5. Backpropagation. And finally 6. How machines learn. Let's just jump right in with section 1. Meet the artificial neuron. From biology to code. So, the perceptron was Frank Rosenblatt's algorithmic attempt to mimic a biological neuron. Think about your own brain. Signals arrive at the dendrites, they build up in the cell body, and if they cross a certain threshold, boom, the neuron fires. The perceptron literally does exactly this, just mathematically. It accumulates input signals, applies a threshold, and essentially decides whether to fire a 1 or just stay silent with a -1.
Now, here's where it gets really interesting. The huge difference between that early perceptron and the later Adeline model is the activation function. The original perceptron used a strict binary unit step function. It fired or it didn't, black and white. But the Adeline, it introduced a continuous linear activation function. Why does that matter so much? Because a linear activation function is differentiable, and that crucially allows us to use calculus, specifically gradient descent, to actually optimize the network over time. It's a real game changer.
Moving right along to section 2, the forward pass, anatomy of a decision. So let's look at this simple 3-layer network. We've got an input layer with 2 neurons, a hidden layer with 2, and an output layer with just 1. We always start training with randomly generated initial weights. You can see them right there, like weight W1 is sitting at 0.11 and W2 is at 0.21. These weights represent the actual strength of the connections between our neurons.
To test this out, we obviously need a data set, and we're keeping it incredibly simple today. We're feeding the inputs 2 and 3 into the network, and our true desired target output for this specific setup is exactly 1. So the ultimate goal? Get the network to look at 2 and 3 and confidently spit out a 1.
Let's run those inputs through. We do this with matrix multiplication, which, by the way, makes programming libraries like NumPy insanely fast in the real world. The inputs multiply by their weights, pass to the hidden layer, multiply by the next set of weights, and sum up. The result? A prediction of 0.191. Well, our target was 1, so this initial random guess is just wildly incorrect.
And that brings us to section 3, calculating the error, facing reality.
So here is the absolute million-dollar question. Our prediction was 0.191, but we really wanted a 1.0. How on earth does the network recognize and fix that massive gap? Because if it's just guessing randomly forever, it's not actually learning, right? We need a concrete, mathematical way to measure exactly how wrong it is. We do that by calculating the difference using a squared error formula. You'll probably notice this 1/2 fraction sitting at the front of the equation. We add that half just as a neat little trick to make the calculus easier to derive later on, since the exponent 2 will cancel it right out. Plugging in our numbers, half times 0.191 minus 1.0 squared, we get a total positive error of 0.327.
Now we've got to figure out how to mathematically shrink that error down, which brings us perfectly to section 4, the gradient descent solution, finding the minimum.
This brilliantly highlights our core problem. We really want to reduce the error, but the actual target output of 1.0 is a constant. We can't change reality. By decomposing our prediction equation, it becomes super obvious that the only elements we actually have the power to change are the weights. Those weights are basically the dials we can turn to adjust that final prediction value.
But how do we know which way to turn those dials? We use an optimization algorithm called gradient descent. It calculates the gradient, or the slope, of the error function with respect to our weights. By taking deliberate steps proportional to the negative gradient, we're essentially climbing down the hill of our error function, searching for that local minimum where the error is at its absolute lowest.
Let's see how this works in reverse. Section 5. Backpropagation step by step. Moving backwards.
Backpropagation is where the magic happens. It calculates this gradient by moving backward through the network. To update a weight like W6, right near the output, we use the calculus chain rule. I know it looks a bit complex on screen, but structurally, the partial derivative of the error with respect to W6 is found just by multiplying the derivative of the error with respect to the prediction by the derivative of the prediction with respect to W6. It elegantly boils down to the difference, the delta, multiplied by the hidden layer output. And the beauty is we just apply this exact same mathematical logic backward across the whole network, from the output layer to the hidden layer right back to the inputs. We successfully generate precise update formulas for every single weight. Notice how the delta trickles backward? It allows even the earliest weights, like W1 and W2, to understand exactly how they contributed to that final mistake.
Now, to make sure we don't drastically overcorrect and just completely overshoot our minimum, we introduce a tuning dial called the learning rate. Here, we've smartly guessed a small number, 0.05. By multiplying this learning rate by our derived delta matrix calculations, we subtract that resulting value from our old weights to get our actual, updated numerical weights for the very next attempt.
Which leads us directly to our final section, how machines truly learn, the core loop.
Armed with these shiny new backward-propagated weights, we run a second forward pass through the exact same network. We multiply our inputs of 2 and 3 by the new weights, and look at this result. Our new prediction is 0.26. This is incredibly exciting. It proves the network is actively learning. 0.26 is noticeably closer to our target of 1.0 than that first random guess of 0.191 ever was.
So there it is. We've just witnessed the elegant core learning loop of modern AI. Step 1, initialize your random weights. Step 2, calculate the output via a forward pass and find the error. Step 3, iteratively use backpropagation and gradient descent to update those weights and shrink that error down. You just do this over and over again, over multiple epochs, until the prediction finally matches the target.
To wrap up this explainer, I really want to leave you with this final thought to ponder. We just walked through how a few lines of basic calculus and matrix math can teach a single, tiny artificial neural network to adapt, correct its own mistakes, and actually learn from data. So what happens when we link billions of them together in massive, deep layers? Well, that's exactly how we get the incredibly complex, world-changing AI systems we're seeing everywhere today. Thanks so much for joining me on this mathematical journey.